So here's the example. We have this function 4 plus x cubed plus y cubed minus 3xy. We need to find and classify all the critical points associated with this function. This is a surface. You can treat it as, you can set up z equal f of xy, and so now this becomes three-dimensional, and the surface level will be f of xy equals k. For instance, for a certain value of z, then we have a surface level. But let's take it from here. Let's find out first an expression for the gradient, and then we'll try to zero it, to make it zero. So the partial derivative with respect to x, well, that would be 3x squared minus 3y, right? The partial derivative with respect to y would be 3y squared minus 3x. So we have a little bit of a symmetry here, but also in order to do the second derivative test, bless you, we might as well go ahead and take the second order partial derivative. So fxx will be 6x minus 0, fyy will be 6y minus 0, and fxy, if the second order partial derivative are continuous, then fxy will be the same as fyx. So here's f sub x, or del f del x. So take derivative with respect to y, you get a negative 3. Here's del f del y, take the derivative with respect to x, you get negative 3. And we can see that, we know that those functions are continuous because they are polynomials. So we got all the components here. Let's first find which values lead to the gradient equals 0. So the first condition, the critical point, will be obtained by the gradient of f of xy equal 0, and this is a zero vector. Each component has to equal 0. So the first component is not f of x, but f sub x, or the partial del f del x. That's why I like to write it del f del x, but I already written it as f sub x. I'll keep it this way. Okay, this required that 3x squared minus 3y equals 0, and this required that y equals x squared. Okay, I can live with that. We have a relation here, and the partial derivative with respect to y equals 0. Well, this required that 3y squared minus 3x equals 0, but y is x squared, so it means that if I substitute or replace y with x squared, we have 3x squared minus 3x equals 0. All right, I can see that I can factor 3x out of this. So 3x, and what's left is x cubed minus 1 equals 0. We have two solutions here. One solution is x equal 0, and the other is x equals 1. Okay, so if x equals 0 and x equals 1, then we have critical point of the following values. When x equals 0, so is y, right? And when x equals 1, y equals 1 squared. So we have 0, 0, and 1, 1. So we have 2. And we need now to classify. So we accomplished the first task, is finding critical numbers or critical points. Now we need to classify. So classification. So we'll run the second derivative test, and what are the partial derivatives? Well, we have, where is it in the previous page? So I was a little bit premature. So let's try first let's see, what is the determinant? D equals fxx times fyy minus fxy squared, like so. So in our case, it will be 6x times 6y minus negative 3 squared. So we're looking at 36xy minus 9. Okay? And now, so we have an expression for the determinant, and we can proceed just by replacing values. So let's see, what is d at 0, 0? Well, at 0, 0 we have 0 minus negative 9. So it's negative, so we can say, we know that we have a saddle point. We have condition 3. So saddle point at 0, 0. And now let's check out 1, 1. D at 1, 1 equal 36 minus 9, and we know it's positive. Okay, what about fxx at 1, 1? Okay, fxx at 1, 1 is it was 6x, right? Equals 6, it's positive, so the conclusion that we have a relative minimum at 1, 1. So we found the two critical numbers, and we classified that. We classified each, I'm sorry, critical point. I keep saying critical numbers because normally in Calc 1 we're looking just for the x value, and the x value was a critical number. The point is the xy value. Anyway, let me sketch a graph of the surface and show you the saddle point and the relative minimum. I'm not going to sketch it by hand. That's ridiculous. That's even somebody with artistic skills. So what I'll do, I'll use Maple to graph it. All right. So let me open Maple, and we'll see if we can look at these. So there is the function, and there it is. So we're trying to figure out the 2 points, 0, 0, and you can see 0, 0 right here. Okay. I don't know if you can see the red dot. What I'll do, I'll try to stretch the graph a little bit. So whoa. Okay, I think now you can see it better. All right, do you see the red dot? And the red dot corresponds. We are looking. This is the x-axis, and this red dot corresponds to the x and the y. Let's see. This is the y-axis on the side. Let me turn completely around, and you can see that the red dot is at y equals 0. And you can see that coming on this screen, if you go along this curve, it's on the xz plane, sort of, it's diagonal, but you see that you have a local minimum. On the other hand, from here, you can see that if you go along the yz plane, you do have a maximum. That's why it's a saddle. It's not a relative maximum or minimum. Now let me turn it around. This is a little bit easier to see. You can see the red dot right here. That's where I placed the the relative minimum, and you can see that it corresponds to, this is x equals 1, and if I put it right now, you can see that it's lined up with x equals 1. And if I put it right here, it will line up with y equals 1, which is right here. Imagine this line. So at 1, 1, you have the local minimum, at 1 at 0 0 you have the saddle point.